In Chapter 7, we will be talking about the central limit theorem. In this chapter, we will be learning to apply and interpret the central limit theorem for means, recognize the limitations of the central limit theorem. And this chapter is important to understand because the central limit theorem is what gives us the power to perform the hypothesis tests that we will spend most of the rest of the semester performing. The central limit theorem is one of the most powerful and useful ideas in statistics. It states that if we collect samples of size n with a large enough n, we calculate the mean of each sample and create a histogram of these sample means, then the histogram will be approximately normal or bell-shaped. It does not matter the distribution of the original population. And that's what makes this so great. As long as we're collecting samples of size n with a large enough n, the distribution of those sample means is going to be approximately normally distributed. The key idea is that the distribution of sample means tends to follow a normal distribution. Sample size n should be larger, so at least 30, or data should come from a normal distribution in order to use the central limit theorem. Sampling will always be done with replacement, which means that a sample can be in our data more than once. So we could collect a sample from Joe, and then later on come back and collect the sample from Joe again. If you draw random samples of size n with a large enough n, then the distribution of sample means will be normal, with the following being true. The mean of the sample means will be equal to the mean of the data values. The standard deviation of the sample means will be equal to the mean of the data values divided by the square root of the sample size. Which means our z value would be equal to our sample mean minus the mean of the data values divided by the ratio, the standard deviation of the data values over the square root of the sample size, which is the same as saying the sample mean minus the mean of the sample means divided by the standard deviation of the sample means. Since we know that the distribution of sample means is approximately normal, and we know mu and sigma, we are able to proceed as we did in the last chapter for finding probabilities. We could use the table if we find z, or we can use the calculator as we did before. Again, we will be using the normal CDF and inverse norm functions. Let's take a look at an example here. A manufacturer knows that their items have a normally distributed length, with a mean of 6.7 inches and a standard deviation of 0.7 inches. If 18 items are chosen at random, what is the probability that their mean length is less than 6.3 inches? So, we're thinking about the mean length of these 18 items. Well, the mean length is going to be normally distributed with a mean of 6.7 and a standard deviation of 0.7 divided by the square root of 18. And we're specifically looking for the probability that the sample mean is less than 6.3. So we're using normal CDF. Our lower bound is negative infinity. The upper bound is 6.3, the mean is 6.7, and the standard deviation is 0.7 divided by the square root of 18. Now you can actually type this in there just as we have it here, except for with the negative infinity, typing the negative 1 EE99. But the 0.7 over the square root of 18, you can actually type it in as that. You don't have to simplify it before typing it in. You're going to end up with the probability that the sample mean is less than 6.3 is equal to, rounding to 3 decimal places, 0.008. So example 1, you're being asked a similar question to our previous example, and we have a manufacturer knows that their items have a normally distributed length with a mean of 5.5 inches and a standard deviation of 0.7 inches. If 5 items are chosen at random, what is the probability that their mean length is less than 4.7 inches? Again, we know that our sample means are approximately normally distributed, and we're looking for the probability that our sample mean is less than 4.7. So we're using normal CDF. Since we have less than, our lower bound is negative infinity. The upper bound is 4.7. The mean is 5.5. And the standard deviation is 0.7 divided by the square root of 5. So the probability that the sample mean is less than 4.7, rounding to 4 decimal places here, is approximately 0.0053. Checking out another example here, a manufacturer knows that their items have a normally distributed length with a mean of 17.7 inches and a standard deviation of 1.1 inches. If 10 items are chosen at random, what is the probability that their mean length is less than 16.8 inches? Again, we know it's approximately normally distributed. Using the normal CDF, lower bound of negative infinity, so as you're typing it into your calculator, you're typing negative 1 EE and then 99. Your upper bound is 16.8, mean is 17.7, standard deviation 1.1 divided by the square root of 10. So the probability rounded to 4 decimal places is approximately 0.0048. In example 3, we have a manufacturer that knows their items have a normally distributed lifespan with a mean of 14.8 inches and a standard deviation of 2.7 inches. If you purchase 2 items, what is the probability that their mean life will be longer than 13 years? Again, we know that the items are normally distributed. So even though we have a small sample size, we know that the sample mean is going to be approximately normally distributed with a mean of 14.8 years, standard deviation of 2.7 years divided by the square root of 2. We're looking for the probability that the sample mean is greater than 13. So we have normal CDF, lower bound of 13, upper bound of positive infinity. So 1E99 is what you would type for your calculator. And then your mean is 14.8. Standard deviation is 2.7 divided by the square root of 2. So your probability that it's greater than 13 is going to be approximately 0.8271. A manufacturer knows that their items have a normally distributed lifespan with a mean of 6 years and a standard deviation of 0.7 years. If you purchase 21 items, what is the probability that their mean life will be longer than 6 years? Again, the sample mean is going to be approximately normally distributed. And we find that the probability that the sample mean is greater than 6 is equal to 0.5. Now this one is an interesting example that I do want to spend a little time talking about. We know that the population mean is 6 years. If we were just talking about data values, ignoring that we're using the central limit theorem for a second here, we know the probability of being strictly greater than the mean, is going to be 0.5. The central limit theorem is assuming that our sample means have the same population mean. So the probability that we're greater than the mean should still be 0.5. So it should make sense that we ended up with 0.5 here. It's an interesting result, though, that was worthwhile spending some time talking about. Let's take a look at an example together again. A particular fruit's weights have a mean of 733 grams and a standard deviation of 13 grams. If you pick 54 fruit at random, what is the probability that their mean weight will be between 728 and 738? Now, before we start listing our summary, there's something interesting about this example compared to the previous examples we've been working. In this example, it does not assume that the fruit's weights are normally distributed. But we have a large sample size here. The sample size is larger than 30. So we don't have to have the assumption that the data values were normally distributed in order to use the central limit theorem. All right, well, let's continue with the example then. So we know that the sample means are going to be approximately distributed because we do have a large sample size. So we have normal CDF, a lower bound of 728, upper bound of 738, mean of 733, and a standard deviation of 13 divided by the square root of 54. So we're ending up with a probability of 0.995. In example 5, we have a particular fruit's weights that are normally distributed, and they have a mean of 523 grams and a standard deviation of 8 grams. If you pick 2 fruit at random, what is the probability that their mean weight will be between 538 grams and 539 grams? Again, using the normal CDF function, entering our lower bound and our upper bound, the mean, and then the standard deviation, we come up with the probability is approximately 0.0017. In example 6, a particular fruit's weights are normally distributed and have a mean of 422 grams and a standard deviation of 8 grams. If you pick 6 fruit at random, what is the probability that their mean weight will be between 420 grams and 431 grams? Again, using the normal CDF function, the lower bound, the upper bound, mean, and then standard deviation, we find that the probability of being between 420 and 431 for the sample mean is going to be equal to 0.7269. Let's look at another example together. We have a manufacturer that makes watches with a mean lifespan of 9.2 years and standard deviation of 1.4 years. If 45 items are picked at random, 9% of the time, their mean life will be less than how many years? We can make the assumption that the sample means are normally distributed, and we would use the inverse norm function here. Our area to the left is going to be 0.09. The mean is 9.2. Standard deviation is 1.4 divided by the square root of 45. So 9% of the time, the mean life will be less than 8.92 years. A manufacturer makes watches with a mean lifespan of 7.8 years and a standard deviation of 1.7 years. If 4 items are picked at random, 6% of the time, their mean life will be less than how many years? Making the assumption that it's approximately normal. Again, using the inverse norm function, we'll find that 6% of the time, the mean life will be less than 6.5 years. A manufacturer makes watches with a mean lifespan of 10.9 years and a standard deviation of 1.5 years. If 16 items are picked at random, 5% of the time their mean life will be less than how many years? Again, making the assumption that it's normally distributed. So using the inverse norm function, we have an area of 0.05 to the left, a mean of 10.9, and a standard deviation of 1.5 divided by the square root of 16. So 5% of the time, the mean life will be less than 10.3 years. A particular fruit's weights are normally distributed with a mean of 552 grams and a standard deviation of 33 grams. If you pick 18 fruits at random, then 19% of the time their mean weight will be greater than how many grams? Again, we can assume that it is normally distributed, and we have the area to the right now is 0.19. We need the area to the left though, so let's rewrite it. So we have area to the left. Area to the left would be 0.81. Now we can use the inverse norm function, area to left 0.81, mean, and then standard deviation. And we get that 19% of the time, the mean weight will be greater than 558.83 grams. A particular fruit's weights are normally distributed with a mean of 402 grams and a standard deviation of 14 grams. If you pick 20 fruits at random, then 8% of the time their mean weight will be greater than how many grams? Again, it's normally distributed. We're given an area that's to the right. So we find the area to the left. We use the inverse norm function, area to the left, mean, then standard deviation. And we get that 8% of the time the mean weight will be greater than 406 grams. That's rounding to the nearest gram. A particular fruit's weights are normally distributed with a mean of 683 grams and a standard deviation of 38 grams. If you pick 7 fruits at random, then 18% of the time their mean weight will be greater than how many grams? Again, it's normally distributed. We're given an area that is to the right. So we find the area to the left instead. Area to the left is 0.82. We use the inverse norm function, area to the left, mean, standard deviation. And we get that 18% of the time the mean weight will be greater than 696 grams, rounding to the nearest gram. The central limit theorem is very powerful, but it does have a few limitations. So the central limit theorem works for any distribution as long as the sample is large enough. The less normally distributed that a distribution is, the larger the sample is needed to be for us to use the central limit theorem. Sampling needs to be done with replacement if we're using the central limit theorem. And because the central limit theorem is so powerful, it will allow us to perform hypothesis testing about means, which is doing inferential statistics. That's what this chapter is setting us up to do, is inferential statistics, which is where we will camp out for the rest of the semester.